Here's a mitigation step for now. You can remove the custom smiley directory, then at least my exploit doesn't work anymore. So why did this work? I don't really think that this is just an implementation issue. This is really about a broken protocol, about a protocol which is so complicated even though it does something so simple. And then it uses these encoding schemes where it shouldn't be using them, and you kind of miss the bug because all you see is this base64 encoded stuff. And the funny thing is Microsoft actually messed this up as well in 2004. So that kind of, that shows the point. So you can download stuff now. You can download the binaries you want to exploit. You can now write your stable binary exploit. Nice thing is you can also query the proc file system. So if you're exploiting something that's already running, you can actually try to circumvent ASLR. You can also find out the proxy settings, and there are passwords lying around. You can download accounts XML, and who knows? Maybe there's a password scheme, right? So now, what do you want to execute? What's your shellcode going to be? Well, what you can do now is you can exploit body icons. You can actually send your patched version of Pigeon as a body icon simply by saying, this is my body icon. And then it will be stored on the remote system as a file, SHA-1sum.icn for icon. And then now all your shellcode has to do is move that file to user bin Pigeon, and you have a patched Pigeon which maybe does stuff like, well, every message that comes from this and that user is redirected to the shell, and the output is redirected back, something like that. So that would be nice. About the memory corruption bug, we're not disclosing it here, but we're inviting you to play a game called beer fuzzing. Basically what you do is you meet up with friends, you get entirely wasted, and then you try to implement what I just showed you, the logical exploit, without copying from Wireshark. Whoever does not trip over a memory corruption bug in SLP code wins. Okay. You are now here. You are now inside the network, and on we go. What we now want to do is, ultimately, we want to attack the cache. But we want to be able to send anything we like to the cache, and there's still this internal packet filter. So that's what we're going to try to break. If you want to break something at layer n, it's always best to just look down a few layers and see if you can break things beneath. So what you want to break is on layer 3 and 4. It's IP-based packet filtering, basically. So why not go down to the link layer and see what you can do there? Well, we're assuming that these normal things, op cache, poisoning, MAC flooding, stuff like that, that all does not work. And in reality, it probably does, but let's assume it doesn't, because otherwise it's going to be boring. Instead, what we do is we want to attack the device drivers. So what could there be to attack with Ethernet device drivers? I mean, there isn't much there. It does addressing, error control, stuff like that. But then there's the MTU, and this is very interesting. It's the maximum. Wait a second. It's the maximum transmission unit, and this is the maximum size of a frame that you can have. So why would you specify something like that? Well, here's a problem. We actually share switches. So if you just tell people you can send frames as long as you like, then if you're the little packet and you have to wait for that big packet to just leave the switch, then that's going to take a long while. So that's probably a little voice over IP packet. Okay, so in the past, 1,500 byte, the MTU of Ethernet, made sense. Because in 10 megabit Ethernet, transmitting this took 1.2 milliseconds. But now we are 100 times faster in gigabit Ethernet. So that means, of course, that we should adapt the frame size. And so we kind of did. We have jumbo frames now. The big problem is we also have those old frames as well, so we have a huge mess in our networks today. We have fast Ethernet NICs, those old 100 Mbit NICs, which can only do 1,500 byte. We have gigabit Ethernet NICs, which are capable of doing jumbo frames, but they actually don't. And then we have some which have them enabled, and then again we have some which have them enabled, but only up to 7,000 bytes or something like that. So it's a huge mess, and this is what we're going to attack. Because naturally the question arises, what happens if somebody sends a packet, a frame, which is 2,000 bytes long, to a destination which can only receive 1,900 byte frames? So here's what happens. Usually, if the frames are smaller than the MTU, each frame just gets put into its own little so-called RX buffer, the receive buffer. Now, if the frame is larger than the MTU, it will actually span multiple buffers. So this is not a problem for the controller, because the controller will detect that the difference between two frames, which were just where one was maximum size and the other was little, and one frame which spanned multiple RX buffers. Because between Ethernet frames, there's a tiny gap called the interframe gap. But the driver will actually have to handle this situation where you have a frame spanning multiple RX buffers. Do controllers handle this? Some do, others don't. Okay, so here's a bug we saw this year. It's the E1000, in the E1000 Linux driver, July 2009, and they actually proposed a fix. But the fix doesn't fix, and nobody's reported this, so now we're going to do that. This is the initial bug report. I'm going to read it to you. If we have a spanning packet, so one that goes across multiple buffers, the first part is discarded, but the second part is not. That one's kept. Okay. So now what happens is that if that second part is smaller or equal to 4 in length, we will then subtract 4 to remove the CRC checksum and actually cause an integer underflow. Then we get a bug. But actually, what's happening here? What's happening is that we're taking a frame and we're using the last part of the frame and interpreting it as an extra frame, as a new frame. This used to be payload, and now we're saying this is an independent frame. And that's the actual bug. So there's a cause. It's if we have a spanning packet, the first part is discarded, but the second part is not. And it is interpreted as an independent frame. Okay? And the effect is that if it is smaller than this and that, you get the integer underflow and all the stuff that we understand. So this is the code. There's a logical bug. The only thing that's important is the comments, which basically says, process the last fragment, and down there is the integer underflow. And this is the patch. Okay. So all they did was check whether this would be smaller than 4 bytes. Epic fail. They didn't even understand the bug, and completely misses the point. So Intel actually published an advisory on this, right? So you would have thought, hey, you guys have the documentation. You guys have the Ethernet nerds that made the driver, that made the card. Okay, so why did you not catch this? Epic fail again. What they did was they blindly copied Red Hat's